So the properties are the following. First property, the Lebesgue measure is countable, additive. Second one, if A subset of B such that either M of A is finite or M of B is finite, then M of B minus A is M of B minus M of A. The third one is if E1, E2 and so on, the sequence of measurable sets, then M of limit En equal to limit M of En. So the limit appearing in the left side is the set limit, and the limit appearing in the right side is the sequence of real numbers, limit of the sequence of real numbers. The fourth one, if E1 contained in E2 contained in and so on, and the M of E1 is finite, then M of limit En is limit M of E. Okay, so in the class lo enna paakarom further. Okay, so properties and discussion about Lebesgue measure. Okay, an example. Okay. Now next problem or result. Okay. So that's first one. Show that every non-empty open sets, every open set is measurable. What about its measure? We already know that the outer measure of non-empty open set is positive always. So has positive measure. Okay, the proof is very easy. So that's the proof enna? Proof சொல்ல முடியுமா? யார் சொல்றீங்க? Proof. Proof enna? The set is non-empty. Suppose E is open set. If E is open, let us take it be a non-empty open set. Then it has a number. Let us say that it is x. In x is an interior point. An interior point. Interior point of E. So there is an interval In containing x such that In completely inside E. So In measurable, E measurable. Okay. This In is, we take this open interval, right? In open, there exists an open interval. There exists an open interval I containing x such that I containing. This open interval has some, it has element x, so it must be of positive measure, right? It is in the form, x is in the form x minus epsilon, x plus epsilon, something like this. So the M of I is positive, implies M of E positive. As M of E value is bigger than M of I. every non-empty open set has positive measure. Now we use the result to prove the following theorem. So you can take this as a lemma of the following theorem. Right? The theorem is this. If Q is enumerated as Q1, Q2, etc. Q is a set of all rationals, and G is the set defined by G equal to union n from 1 to infinity Qn minus 1 by n square Qn plus 1 by n square. Then for any closed set F, measure of G delta F is positive. Okay. So G is nothing but union of this. For each rational, we consider the open interval Qn minus 1 by n square, Qn plus 1 by n square, Qn plus 1 by n square, union of all the. So this G contains all the rationals. What about G bar? It is exactly R. Plus G contains all the rational. Closure of the rational is real. Set of all real numbers. So for any closed set F, measure of G delta F is positive. The proof of this. From the previous result, that every non-empty open set has positive measure. If an open set has a zero measure, then the set is empty, right? By the contrapositive statement of negation of that. Okay. So we let us take two cases. What about, we recall what is the meaning of, recall that G delta F is nothing but G minus F union F minus G. Right? Suppose if measure of G minus F is positive, then so obviously measure of G delta F is positive. Right? So on the other hand, if F of G minus F is 0, then G is a countable union of open interval, so G is open, F is closed. Right? What about G minus F? G minus F is since, okay, by the nature of G and F, since G minus F is open, then G minus is open and its measure is 0. So by the previous result, this set is empty by the previous result. If G minus F, this implies G minus F is empty, means what? G minus F is empty. Empty means what? There is no X in G such that X does not belong to F. There is no number in C. Right? Elements of G not in. This means what? Every element of G, okay, must be, the negation of this statement is for all X in G, X belongs to F, right? Implies G is a subset of F. right? Elements of G not in F, nothing. Okay, so F is closed, but G contained in F. What about G bar? G bar contained in F itself, because F is closed, therefore F equal to F. Okay, G bar is, since set of all Q contained in G, so Q is contained in G. What about the Q bar? Q bar is R, and Q bar is R. So from these three relations, we take F equal to exactly. Okay. இப்ப G bar F Q G ல இருக்கு இல்லையா? Q is contained in G. Q bar contained in G bar. Q bar contained in G bar. So G bar is okay. Q bar, everything subset of R. So Q bar is R means okay. G bar is exactly R. G bar is R means F is also R. It's equal to R. Equal. And Q bar is contained in G bar, in place F is. So what about measure of F? Equal to infinity. Okay. Measure of F is when measure of F minus G is 0, measure of F is infinity. What about measure of G? By the definition of G, measure of G is less than or equal to measure of union Qn minus 1 by n square, comma Qn plus 1 by n square is less than or equal to summation n from 1 to infinity, measure of Qn minus 1 by n square, comma Qn plus 1 by n square. So this open interval has measured open interval Q minus 1 by n square, Q plus 1 by n square has measured 1 by n square is 2 times. Right? 2 times. 2 can be taken outside, Then we have the exactly the sum of 1 by n square. This series converges, so it is finite. So the only information we know we need is the summation must be finite. Measure of, we don't want the exact summation. Measure of G is finite. So measure of G finite, right? The property of M is the following. If A, what is the second property? If A is subset of B, either M of A finite or M of B finite. If any one of them is finite, then M of B minus A can be written as M of B minus M of A. So I am going to use that result here. Since G is a subset of F and the measure of G is finite, so measure of F minus G equal to measure of F minus measure of G. So what's the measure of F? Infinity is finite, right? Infinity minus a number, infinity. So it is positive. And M of G minus F is 0. Okay, the other side has infinite measure. Therefore, M of G delta F has positive measure. Okay. Now we prove that already we know every countable set has zero outer measure. Countable set is closed. Countable set you cannot write that. Countable set has measure zero, outer measure 0. If a set has outer measure 0, then it is measurable. Right? So I can write the following statement. Every countable set is measurable. So exercise. Every countable set is measurable and it has zero measure.